Hi everyone. In this session we'll see some problems that are related to the introductory section of my lectures in previous lectures. So let's start by just trying to do some loose structures. So if you are given a C4, a C2 actually, a C2H4O structure or formula, you're required to write some loose structures. So the loose structures can be various constitutional isomers. That means the constitutional isomers would end up to be different compounds. So we expect from this, by just putting C as a central atom, another C which has 2 electrons for the bonding. If you were to put each one of the electrons, we are trying to put it in a sigma like this. So if you have one hydrogen here from 2 electrons again, another hydrogen, now you are left with another hydrogen. You have accounted for the 3 of the hydrogens. Now we are left with 1 hydrogen and also 1 oxygen. So the only way this can have a bonding situation would be, let's say you have a hydrogen here, and now the octet around carbon, as you see, it still needs 4 more electrons. To accommodate 4 more electrons with oxygen, for example, if we just put 2 and oxygen here, that would satisfy what we need, basically. So you need to check each one of these centers, like carbon, oxygen, if they have satisfied the octet rule. So this is one of the constitutional isomer which satisfies C2H4O. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So this is a good loose structure for C2H4O. But this formula can be also differently constituted, so that it gives another constitutional isomer. So the way we could draw this could be, for example, if we have C, one of the C and another C, in this case, now you see there is a double bond between the 2 carbons. So as I already told you, now 1, 2, 3, 4 hydrogens, and now you would have 2 more, for example, here a hydrogen, here a hydrogen. So now the octet is satisfied for this structure for carbon. 1, 2, 3, 4, 5, 6, 7, 8. How about for the other carbon? Now what we are left is 2 hydrogens and 1 oxygen. How can you put 1 hydrogen and 1 oxygen? So 2 hydrogens. 1 hydrogen can be seated here, and the other can be like this. So if you just count around each atom, whether its octet rule is satisfied or not, you have 1, 2, 3, 4, 5, 6, 7, 8. That's octet satisfied for this carbon. How about for this carbon? 1, 2, 3, 4, 5, 6, 7, 8. How about oxygen? 1, 2, 3, 4, 5, 6, 7, 8. All are neutral, no charge on them, and the octet rule is satisfied. To tell you the truth, there would be 1 more actually isomer as well. These are called constitutional isomers. So don't forget what we have covered in constitutional isomers. Compounds that have the same molecular formula but differently constituted in their arrangement or in their loose structure. So the next one I would suggest would be a carbon-carbon, and think of a ring. We have only 2 carbons, and they could be situated like this. But if you have a ring, it can only make a ring through oxygen. Therefore, if you just put it there, now you have 4 hydrogens. That means 2 on this side, 2 on the other side. This is also a structure. So this compound, if you just try to see if octet rule is satisfied, all of them are octet satisfied. If you see 1, 2, 3, 4, 5, 6, 7, 8 for this carbon. For this carbon, you have 1, 2, 3, 4, 5, 6, 7, 8. How about oxygen? You have 1, 2, 3, 4, 5, 6, 7, 8, including the lone pairs. So there are lone pairs on oxygen, obviously. Don't forget, in most cases, oxygen carries 2 pairs of lone pairs. So now, as you see, these are the same formula, C2H4O. All of them are C2H4O. This is C2H4O. This is also C2H4O. This is C2H4O. These are differently constituted. They are not the same compounds. They are not related. Even though they have the same chemical formula, they are different. Compounds that have the same chemical formula but different how they bonded to each other are called constitutional isomers. The relationship between all of this, they are just constitutional isomers. And they are different compounds. They have different physical and chemical properties. So in this problem, we solved the loose structure for 3 constitutional isomers which came out of C2H4O formula. So don't forget, even though they have the same chemical formula, they are differently constituted and they are different compounds. They have different physical and chemical properties. Different physical and chemical properties. All right, so we'll move to the second problem. Okay, in this problem, what we see are different structures of compounds. And the question is, what is their relationship to this compound? Let's say this is called compound A, which has a molecular formula of C7H9O. How are they related? Are they constitutional isomers, or what they are? Are they resonance structures to one another? So that's what we're gonna answer in the next problem. So the question is, what is the relationship of all these structures to compound A? As you see, all of them are C7H9O, C7H9O, C7H. All of them have the same chemical formula. But as you see, we could find that they may be not even related to compound A. So let's examine first compound B. Compound B, how is it related to compound A? As you see, C7H9O, there is carbon here, there is oxygen, there is a double bond, there is a double bond. So there is double bond here at this position, there is one CH3 here. So remember, this means CH3. Here, each one of this there are 2 hydrogens on this, one in, one out. Remember, in sp3 hybridized carbon, there are 2 hydrogens in this. Similarly, there are 2 hydrogens here. The same thing here, but at the double bond, remember, at the double bond, you have only one planar hydrogen. that is 120 degrees oriented. So here you have also, remember, there are hydrogens. So the skeletal form, what you see here, you should remember that how many hydrogens there are. In terms of hydrogen, C7H9O, they are the same, but they are differently configured. At this CH3, there is a double bond here in this one, but this one doesn't have. Therefore, the relationship, the double bond actually is shifted on this side, on this compound. Therefore, this and this compounds are isomers. They are not related. They are constitutional isomers. The reason being, the double bond right here, what you see is not in the same position as this one. So it is differently bonded. When we say constitutional isomers, we have already said that the bonding pattern is different in constitutional isomers. Even though structurally and chemical formula wise they are the same, they look the same, but the double bond position is next to the metal group. This is CH3. So therefore A and B are constitutional isomers. How about this compound right here? This compound actually is not C7H9. I made a mistake. This compound is C7H11O. If you just count all of the hydrogens and the carbons, this is C7H11O. Make sure that I gave you the right formula. C7H11O. One carbon here with 3 hydrogens. One hydrogen right there. 3, 4. 6, 8, 8, and there are 10 here. Actually, it is 12. 3, 4, 6, 8, 10, 12. So it is a C7H12O compound. So they should not be related at all. They are not even constitutional isomers. So this is neither, because the formula here is C7H9O. The formula here is C7H12O. That means this compound doesn't have the double bond, which this compound has. Whenever you make a double bond, 2 hydrogens are replaced. That's why the C7H9, I think here also this should be C7H10 actually. C7H10O, otherwise we just eliminated 2 hydrogens. 3, 4, 6, 8, 10. So this is a C7H10O compound. My mistake. So in this one, it is C7H12O. That means they are not even related. So we call in this case neither constitutional isomer or resonance, so they are not related at all. Let's say this is compound C. Compound C is not related at all to compound A, because compound C doesn't have even the double bond. Here in compound B, the double bond is in a different position. That's why they are isomers. They are constitutional isomers. Okay, let's evaluate the compound D, that is C7H10O. So at this point, you should be careful to say that whether they are related or what their relationship is. C7H10O is, it looks like it has a charged species, but the charges are a plus and a minus, so it doesn't mean in terms of charge, this is, even though it's neutral, this is also can be neutral. So what does the charge created? So let me redraw compound D again. Compound D is redrawn as and the bond is here and there is a charge. So if you just look at this and draw a resonance structure, you would look that, or you end up saying, oh, they are the same compound actually. So the relationship is one is the resonance structure of the other. So if we just push pair of electrons to this, carbon cannot accommodate more than 4 bonds. This bond should be moved to this. The plus charge is now satisfied. It becomes 0. So the resonance actually looks like and actually you have this. Now if you just look at this relationship, this is exactly this. That means compound A and compound D are the same compounds. They are the same. They are just one is the resonance structure of the other. As I already told you in the resonance structure, which one would be a major contributor, this is a major contributor because there is no charge on it. This has a charge separation, so it would be a minor contributor between the two. So we are learning more than one concept here. Compound D is a resonance structure of compound A. That means the resonance doesn't alter the property of the molecule. They are the same because they are hybrid of all of these structures. Therefore, a resonance structure, they are the same compound. Compound A and compound D are same molecule. Same molecule, but the relationship is that compound D here is a resonance structure of compound A. So that's the relationship they have. So they are the same compound, but just the way it is written here, if you just push the electrons, you end up to this. So A and D are just resonance related, same molecule. Resonance structures are same molecule, but different electronic distribution. How about C7H10O? If you just count, this is C7H10O, immediately it is obvious that the compound is differently constituted. If I say compound E, actually the ring is contracted into from 6-membered ring. This is 6 carbons around the ring. Here you have only 5. 1, 2, 3, 4, 5, and double bond CH2. So these are differently constituted. They have the same molecular formula. Therefore, compound A is related to E just as a constitutional isomer. Constitutional isomer. They are not the same molecule, they are different molecule. The only thing what they have in common is they have the same formula, but they are differently configured the way how the loose structure or the structure is composed of. This is a 5-member ring, so it's immediately you can just say this is a 6-membered. So the bonds that are making the C7H10O are not the same in compound A and compound E. So as a review, compound A and compound B are constitutional isomers. Compound A and compound C are not even totally related, so they are neither constitutional isomer or a resonance structure. Of course, you cannot have resonance when everything is a single bond here. But compound A and compound D are resonance related. They are resonance, the same compounds. So the resonance structure looks like this. And compound A and compound E are not related as resonance, but since they have the same molecular formula, they are related as constitutional isomers. They have different physical and chemical properties. So we'll continue to the next problem. Okay, continuing our discussion on some of the problem sets we have, let's draw a structure for C3H8O and show what relationship they have between those compounds. So for example, if you have C3, let's put them as a chain first, the 3 carbons. Now we can write the hydrogens because we have 8 of them. I can have this, I can have this, but now what's remaining is I have 5 hydrogens that have in place, but there are 3 more that I need, and oxygen obviously. So if you just put oxygen on hydrogen, you take care of 1. You should always make a bond between carbon and oxygen. And if you add 2 hydrogens, now you are able to draw the C3H8O. So this is another one constitutional isomer for C3H8O. But this is not the only constitutional isomer you can have. Another constitutional isomer that we could write would be by just putting oxygen in between the 2 carbons, for example. That would be if you have carbon, oxygen, carbon, carbon. So this is the arrangement I propose just to solve the problem. So putting the oxygen in between the carbons. So at this point, this would be 1 hydrogen right there, 1 hydrogen, 1 hydrogen. Oxygen, obviously, you should remember there are 2 lone pairs because it should satisfy the octet rule. This carbon can take 2 hydrogens, and this carbon can take 3 hydrogens. So if we just count the number of hydrogens, you have 3, 5, 8. So we are good with 8 hydrogens. So this is a C3H8O constitutional isomer to one another. So the relationship between, for example, let's say A and B, they are isomers. They are not similar compounds. They are just isomers because the configuration of the bonding in each atom is different from this one. For example, you have carbon, next is carbon, here you have carbon, there is oxygen. So immediately you can just rule out that they are not the same compounds, except they can be called constitutional isomers. In the next problem, the question is, what is the relationship? If you just look at this is C5H9. C5H9, obviously I have a negative charge. Just to show you, this is a charged molecule. So what is their relationship? The relationship is you have to check. If you just look at here, the carbon-carbon double bond is right here, but the carbon-carbon double bond is on this position. But you have to also think of a resonance. Can I draw a resonance structure? Because whenever you see a double bond and a pair of electrons, there is a possibility that they might be resonance related. So if I just put a sign or a symbol for resonance and start pushing electrons, what do I get? For example, if I put these 2 electrons back to the bonding here, the bond right there, the way this is, I would take out this. Obviously the carbon cannot carry here more than 4 bonds. The pair of electrons would be out of the bonding situation. So exactly what you see here is this. The electrons are pushed to make a double bond, and those double bonds are now become a single bond by pushing out the pair of electrons, and the charge is residing on this carbon. So these 2 molecules, as you see, are resonance structures. So they are the same compound. The only relationship they have is they are resonance to one another. So same compound, but resonance stabilized. So remember to exercise whenever there are bonding situations where the atoms are not in the same order that you see. Immediately what comes to your mind should be isomers that are constitutional isomers, and immediately when you see a double bond and the double bond has moved somewhere else, immediately you should think of a resonance structure. So the resonance should be, for example, if I give you another structure, don't be confused, if the double bond is somewhere else that cannot be justified by resonance movement, those compounds would be also different compounds. But resonance structures are chemical formula way, they are the same, and the only thing they are different is the pi bond distribution, or the double bond is moved because of electron movement. So this is an electron movement, or charges are moved. Atoms are not allowed to move just by the rule for resonance. This is just shows you an electron movement that we call resonance. So if I call this is C and this is D, C and D are the same molecule, but they are just showing a resonance hybrid of the structure. All right, here the problems are, these two problems are given, two molecules, and you are required to draw a resonance structure. As you see, these are resonance symbols. So what is a resonance structure? Remember, a resonance structure can be more than two. You can have more than 2, 3, 4 resonance structure for a given molecule. But here the problem is asking you for compound A and B to draw a resonance structure. As you know, the resonance structure starts by electron movement. So if we were to move electrons in this structure, the first thing, for example, if I move a pair of electrons from oxygen to this carbon, just look at this and see the electron movement and the steps I'm taking. Immediately this carbon cannot accommodate more than 4 bonds, so this pair would go to this, and when it makes this double bond, since electron pairs are coming, the charge would be gone. So what does it look like? The structure looks like CH3, CO, no, CH, CH2, and I have CH. So this is what it looks like. Now a neutral species is formed. So that's one of the resonance structures. How about if I just move a pair of electrons to oxygen and just leave this here? That would be a plus and a minus. As you see, there is a neutral one. So another resonance can be just move this to that oxygen. The resonance looks like CH3, CO, O minus, and a plus, because you have moved out. And if you calculate the formal charge, that should be a plus. CH, CH2. This is another resonance structure. Starting from here, that is the resonance possible, that resonance is possible as well. How about another one? For example, if you were to move from this system, resonance can be continuous, or you can just do it in different arrows. For example, if you were to move this pair of electrons to this carbon, now you'll end up having CH3, CO, CH, a plus, and CH2, a negative. So remember, I haven't moved any of the atoms. These are the different structures, resonance structures for this molecule. But as I already want to tell you, this molecule, because it has a minus and a plus, actually it can achieve a neutral resonance structure, which is this one. And also you can have charge separated structures. So the most important thing I want to tell you here is the most important resonance contributor, the major one, is this structure. This is a major contributor. Major contributor. Because the reason why I'm saying this is a major contributor is there is no charge on it. Remember the resonance rules. The one which has the least charge species would be a major contributor in a resonance structure. Second, if you just look at this, a negative charge is on oxygen here. The charge is separated, even though one is on a plus on carbon, here is a plus on carbon, oxygen is negatively charged. Comparing these two, remember this is an important concept. Having a negative charge on oxygen is a good thing because oxygen is more electronegative. That means it can carry a negative charge comfortably. So in these two, when we compare these two, the negative charge is on oxygen. That is fine in terms of comparing the two. The only difference in these two is the charges are highly separated. That means the plus charge is 1 carbon, 2 carbon away from the oxygen. So it becomes, this would be the next major. So in terms of assigning major 1, major contributor, the next contributor 2, this is how I assign, because if you compare with 2, the negative charge is fine, it is on oxygen. A resonance structure that puts a negative charge on a more electronegative atom is preferable. But the only difference between these two is the two charges are separated, highly separated here. But here also, if you just look at, so the next I would say would be 3 would be this, second would be this, second major, third major. The least one would be this, I would say, because the negative charge is on more electropositive atom. Carbon is, if you remember, the electronegativity scale for carbon is 2.2. So the negative charge, which is this charge, doesn't like to stay on carbon. I already told you negative charges are fine when they are on chlorine, on oxygen, on nitrogen, etc., but not on carbon. So this would be the least contributor. I would put it as a 4. Major, and the least contributor would be that resonance. But all of them are resonance structure. No atom is moved. So how many resonance structure we draw for this? 1, 2, 3, 4 resonance structure. So whenever you are asked to draw a resonance structure, make sure that you are drawing exhaustively all of the resonance that are possible. Let me do a resonance for structure B. When we do a structure for this, the first thing is, as I already mentioned to you, it would be electron movement. When I say electron movement, if you have this, let's say first move just this and satisfy the positive charge to be neutralized. That means you have NH2, but now you are leaving you are leaving there is a charge here. There is a charge here. That's what our molecule would be. Now, if I just move that, and you have charged species here, what you'll end up would be a plus on this carbon. But if you just move this again, this pair of electrons, so we are starting from this, if we remove pair of this, we'll end up having this resonance structure, NH2 with a double bond here, because I moved a pair of electrons and the charge is satisfied. Obviously, don't forget this, because we started with this, so you cannot just remove electrons. Now, the other possible resonance structure would be, for example, if I have this pair of electrons, always remember the nitrogen should have always one lone pair on it in a neutral molecule. Oxygen should have two lone pair electrons. So if you were to move this back again, this comes out. Instead of coming out, you can bring it here, and this can come out. So what you have is, since the lone pairs are donated to make a bond, NH2, now you have nitrogen plus, because the lone pairs that are bound to nitrogen are making a bond. So the double bond now is moved here, and lone pair of electrons are on this. And this is still there. Right? Let me make sure I made any mistakes on this. So you have a pair of electrons that's making that, and satisfied. Okay, now we can also still play with this resonance structure. If I just move this pair of electrons to this bond, this can move here, and that can satisfy that. So the resonance structure looks like you have a double bond, which is still there, you have a double bond here, you have a double bond here, you have NH2. So if you just look at these structures, we have 1, 2, 3, 4, 5. There might be more, so you have to exhaustively do your accounting for the resonance structure. So basically this and this are the same, so there is no difference, except you can just move electrons. They are almost the same by moving different electrons. So the major one, the major contributor are, this structure is a major contributor. So this is major. The reason why this is a major contributor is it doesn't have charge on it. Even though, so you started from a compound, you have a minus and a plus. Remember, even though the electrons are in different places, the overall charge in this is zero charge. So it is not violating any of what we come up with. So this is a neutral molecule with no charge, so it would be a major contributor. So the most minor contributor would be, some of them would be equivalent. So having negative charge on carbon is not preferable, so they are almost equal contributors. Equal contributor by having just a negative charge on this carbon, on that carbon, on that carbon. So, but the major contributor for this structure, if we just go directly to this, the way it would look like is just move these electrons back, that comes out, so they are directly, this is a major contributor. So you can achieve it directly to this from this. For example, if you have a resonance for this, You just move this pair of electrons to this, that comes out and makes a neutral NH2. I don't want to complicate this, that's how we moved. So the electrons were just moved to this nitrogen in the initial. So it doesn't matter whichever way you go, as long as you exhaustively account for all the resonance structures. So this is the most major contributor for this compound. Okay, so the next problem what we have is to draw resonance structure for this compound. As you see, this is a symbol for resonance structure, and show what is the major contributor for this resonance. So if you just look at where we can do the resonance structure would be, these lone pairs are important, this double bond is important, so we start by just moving electrons in the structure. So if you have moving this, you are trying to have this bond to come up and reside on carbon. So the structure looks like out of that would be CH3, C, CH3, pair of electrons as a negative charge, and you have a nitrogen which has a double bond now, NH2, since it is using its lone pair, you have a plus charge, and it's correct that this started a neutral molecule which is zero charge. You have also a zero charge, except they are just created charge separated in the resonance structure. So this is one way of just drawing the resonance structure. The next one would look like, if we were to draw a resonance for this, for example, if you just take it from this one is the first one is just moving the pair of electrons starting from nitrogen, you are moving all the way. But if you have to write a resonance, again another resonance where you are just moving the pair of electrons on nitrogen instead of just having the double bond here, if you just put them as a lone pair on nitrogen, I don't want to write another arrow so that you don't get confused, but what happens is if you just pull out this pair of electrons from carbon and put them this on the nitrogen, that means nitrogen would carry two lone pairs and negative charge. You have NH2, same structure, and carbon is now plus because it gave a pair of electrons to nitrogen, CH3, CH3. It looks like this. So this is another resonance which came by just moving a pair of from the bonding carbon-nitrogen bond, one of the pi bonds are removed and just you put them on nitrogen, the pair as a lone pair. Now the question becomes, what is a major contributor? Obviously the major contributor is your starting material, your starting compound is major because there is no any charge separation on it. So in the second case of the next major, or if you just put them as number one scale, I would say in terms of charge separation, this is charge separated and the negative charge is on carbon. So it may not be a very good resonance structure, meaning it would not be a second major. The reason being, charge is separated by one more nitrogen. Here charge is very close. In addition to that, carbon is carrying a plus charge, right? In this case, carbon is carrying a negative charge. Remember I told you negative charges are very comfortable on oxygen or nitrogen, etc. So I would say this would be the next major. This would be the least contributor, R3. Reason being, the charges are separated widely, The charges are close here. In addition to that, carbon is carrying a negative charge. Instead of carbon carrying a negative charge, if it was positive, that would be a different story. So remember now how to draw resonance structure and how to assign a major and a minor contributor. In some cases, they would be equivalent. So this was A, B. The question in this R, there are 1, 2, 3, 4, 5 molecules. So the question is, what is the geometry of this carbon, for example? What is the geometry of that carbon? What is the geometry of that carbon and this carbon or any of the other carbon? What is the geometry of that carbon? When I say geometry, it implies hybridization as well. So what is here or what is there? So what is the geometry is, if you just look at carbon right here, it is an sp3 hybridized carbon. It has 4 lobes, 4 atoms that are attached to carbon. Group 1, group here, another group 2, and the 2 hydrogens are here. So the only bonding situation that can accommodate 4 atoms around carbon is tetrahedral geometry. So carbon around that has a tetrahedral geometry. So if I were to draw this, that carbon, for that carbon, it is sp3 hybridized orbital. For that matter, all of them are sp3. This is sp3, this is sp3, this is sp3. All of them are sp3. But if I were to draw a tetrahedral geometry for this carbon, it would look like that carbon in the middle. Remember, there are 2 atoms, 2 groups that should be on the plane of the board. 1 hydrogen. If I put this hydrogen on the plane of the board, and if I put the metal group on the board, also CH3, and now this group and that hydrogen would be in and out. So for out, for example, I can just write down this wedge form, CH2, CH3. But this hydrogen would be now to the plane of the board. So remember to review the section where I was discussing a tetrahedral geometry. So this is sp3 carbon. Always a sp3 hybrid orbital would have a tetrahedral geometry. This is tetrahedral, and sp3 hybridized. So for that matter, this molecule, this carbon is sp3 hybridized. Therefore, it is tetrahedral at this point. Also, if you were to draw this, this is obviously sp3, sp3, sp3. All of them are sp3. Now, the next question is, how about this molecule? This molecule has sp3 hybrid orbital on this carbon is sp3, therefore 109.5, remember, also the angle, 0.5 degrees. So that is sp3. This is sp3. It's a single, all of them are a single bond. And remember, there are hydrogens. Don't forget when we abbreviate this. There are 2 hydrogens. There are 2 hydrogens in sp3 hybrid carbon. This is sp3 as well. This is sp3 as well. But this carbon is carrying a double bond. This carbon is a double bond. Whenever you have a pi bond, it is made of 1 sigma and 1 pi bond. The pi bond is the result of a pp interaction to make a pi bond. Therefore, it has to be an sp2 hybrid orbital. Review the other section where I was discussing about sp2. So this carbon with double bond is sp2. This is sp2. Of course, the sp2 has only 1 hydrogen on it, not 2 hydrogens like sp3. And the angle is 120 degrees. 120 degrees for sp2. Here, this carbon right here is sp3, sp3, there is no double bond, sp3 with 2 hydrogens in each one of those, sp3, sp3. But this carbon right here with oxygen has a double bond. This double bond is a result of 1 sigma and 1 pi orbital bonding. Therefore, this is sp2. Don't forget that. The oxygen is also, since it's bonded with the pi bond, is sp2 hybridized oxygen. So the bond angle here is 120 degrees. Obviously now this carbon is sp3 because it has 4 bonds attached to it, 3 hydrogens and 1 bond, sp3. But that carbon right there has a sigma and a pi orbital. Therefore, a double bond is sp2. Next, this compound right here is 3 bonds around a carbon-carbon bond. If you just look at this is 1 sigma and 2 pi bonds. A 1 sigma and 2 pi bonds around the carbon-carbon is a sign that you have sp hybridization. So the 2 carbons are sp hybridized. So whenever you have a triple bond, an alkyne, a triple bond, the hybridization would be sp. So review the sp hybridization, what it means. It contains 2 pi orbitals. This carbon with a double bond to nitrogen should be sp2. We have already discussed that. This nitrogen with a double bond should be sp2. This one should be sp3 with all single bonds. So this is an important concept that you need to practice more and more, and you'll find the review lecture in previous sections. I have 2 concepts here, bond length and dipole moment. These problems would show you how bond length is applied and dipole moment as well. Here we are asked to compare the carbon-carbon bond lengths. Here the carbon-carbon bond lengths, and also let me redraw this structure. Actually it should be CH2 and this. So if you are asked the bond length between this carbon-carbon and this carbon-carbon bond, it's obvious from their hybridizations, you can tell which one is shorter and which one is longer. So if you just look at the question is on these 2 carbons and that carbon bond length, the carbon here is sp hybridized, triple bond around the across the 2 carbons. Here this is a double bond, sp2 hybrid carbons. Now if you just look at from what our discussion was last time, an sp-sp hybridized carbon bond between the 2 carbons and the triple bond is the shortest. The next carbon-carbon double bond is short. And if you have, for example, a single bond like this, CH3, no, CH2, CH3, between this carbon, that is longest or long. So if you just to compare, this is sp3 hybridized, that's why, sp3 hybridized. So remember, in this review, a carbon-carbon triple bond is the shortest and the strongest bond. The next short one would be carbon-carbon double bond, and the longest or the long bond would be this carbon-carbon bond between 2 sp3 single bond. So this is single bond, this is double bond, and Here, this is a triple bond. As a review, remember we have across the carbon-carbon bond, there are 2 pi orbitals and 1 sigma across the carbon-carbon. I'm not considering the rest. Here between these 2 carbons, there is 1 sigma and 1 pi bond. Here everything is sigma bond. Everything is 1 sigma bond between these 2 carbon, the carbon-carbon bond. Here I am considering just the carbon-carbon bond as well. So remember, this is referring to bond lengths as it relates to hybridization and also the strength of the bond. In our last discussion in the problem set 1, I will just show you dipole moment, which is important in when you determine if a compound is polar covalent or non-polar and etc. So the most important thing is that dipole moment is a result of charge or electronegativity difference between 2 atoms, and also in the overall molecule, the vector sum of the dipole moment, what makes it overall if the compound is polar or non-polar. For example, here you have CHBr3. So if you draw the tetrahedral, this is tetrahedral because carbon is attached to 4 atoms, therefore it should be tetrahedral. So when I draw a tetrahedral, I have my Br here, and then one of the Br here, another Br into the plane of the board. So if you were to see this compound, whether it is polar, obviously between carbon and bromine there is electronegativity difference, so sigma plus would be here, this is sigma negative. That means it's showing you the dipole moment is showing you a vector like that. Here also sigma negative and sigma positive, obviously you have that. And here the Br is also pointing towards Br, the dipole moment, this is sigma negative. So if you just look at here, there are 2 downwards pull by the vector sum. This compound is a polar covalent. It's polar covalent because the dipole moments, they don't cancel out. The only one is the other side. So if this is cancelled, for example, because they are opposing, you have a net dipole moment because of the net dipole moment that is present. How about CBr4? That means just replacing the hydrogen with 1 Br, 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 Br. So this is looks, whenever you see this much electronegative atoms around it, of course the bonds are polar because there is still a charge of negative on positive on carbon, negative on bromine, charge density. Therefore the dipole moment pulls it that way, the dipole moment is that way, but dipole moment that way. Even though we have all these bromines on it and with all this dipole moment around it, because they are vector sum of all of those, they cancel out. Therefore this is non-polar covalent, but the bonds are polar covalent, each one of them, but as a whole for the molecule it is a non-polar covalent because the dipole moment cancels out in all directions. Now if we're also to compare in this molecule, remember carbon-chlorine bond is a polar bond, carbon-chlorine is a polar bond. Therefore, this carries a sigma negative, this carries a sigma positive. This is also So the dipole moment points that way, the dipole moment points that way, sigma positive, sigma negative. So the dipole moments are showing in one direction, so they are additive. Therefore, this compound would be, actually I should have this and that. So actually this compound is polar covalent compound. But if you see here, say we didn't have this, let's say that bond and this, if we were to compare these two, for example, the only thing what you see here is the dipole moment is pointing that way, sigma negative, sigma positive. Here the dipole moment is showing this much, almost similar, carbon-chlorine bond, sigma negative, positive and sigma negative. As you see, the vector sum of these two dipole moments cancel out to be 0. Therefore, this one is a non-polar covalent bond. This is a polar covalent bond. So you can compare the polarity of a compound by just the addition of the dipole moment. Here the concept is understanding dipole moment. That means electronegativity difference along the carbon X bond. If you have an X atom here, what is the electronegativity difference between the two? Usually carbon stays as a positive, but whatever heteroatom you have would carry a negative charge. So if there is a large difference between these two in electronegativity scale, that bond is a polar covalent bond. So we just finished a review of problem set 1, and we'll continue in the next problem set next time.